everyone kind of caught this image where they could see the toe box pointing up like that. And that caused a stir out there on the internet of everyone speculating whether A, that this was new, and B, it must be actuated, because the only way that thing could be going up is it had to be actuated. Okay. I'm here to tell you it's not. All right. It's not actuated. And I put a post out there just saying there's been a big flap over a flap. It's articulated. Okay. Not actuated. Full stop. Why? And it just comes down to physics. Okay. It's simple as that. We'll go through it. We'll explain why that is, and for many, many reasons. And at the very end, I think we will actually have the final nail in the coffin. This is a part of a post I put out that for some reason is going crazy right now. It's got like over 100,000 views, in which just reminding everyone that in December 2023, when the Gen 2 bot was revealed, this is one of the images right from there where they say articulated toe sections. They didn't say actuated, they said articulated. Articulated means it's able to move. It's got a hinge in there of some sort, and it has something to put it back in place, probably a torsion spring or something like that. Some sort of flexible unit that'll do it. And you can see right here the angle that the toe box makes back there, which is why they put that in there at that point. We were already seeing that Optimus could walk that way. There was a lot of skepticism on whether they should use RL for walking. And then others were doing it in Unitree, and those were demonstrating, hey, this works. And then everyone said, okay, maybe we should start to pivot in that direction. So it looks like because the modeling was so challenging, it took a while before they get to the RL.
I want to understand
Yeah.
the part of the actuator modeling they made in-house. What was
Mhm.
the challenge? Did you have maybe, like, you mentioned a couple of things.
Oh, yeah. Well, okay. The first thing, like just these Heim joints are sloppy. Just modeling that right, that when you apply the force down here and going through there, what's the articulation going to be like? Saying exactly what that's supposed to be. So you have to model everything here correctly in the geometry. So it's partly a trigonometric issue. And then when you go up to the knee, it's even more complicated. What are the reasons that you want to have an articulated joint? So the Gen 1 of not only Optimus, but many of the other bots out there, they just had a flat foot. No articulation at all, just because they were getting it out. Everyone was pointing out, oh, why don't you have something that's flexible and this and that, or putting on different shoes. And as you can see, I have a flat foot on a flat surface, and the force is evenly distributed over the entire surface area of the foot. Now, as soon as I start to change the angle, like lift up my heel just a little bit, so I have a non-zero angle, the smallest angle, no matter what it is, will instantaneously result in this. At that instant, you go from full contact to contact along an edge or a point, but edge and a point is the same thing. One's 0 dimension, the other one's 1 dimension. They have no area. So that means all your forces being right there, you're going to slip. You're just going to slide right away. So you don't want to have a point of contact. You want to have a surface of contact going on there. And so the reason for having the articulation is now when you do that, look, you've got all this, which means you're not going to slip. From this, I'll go to here to this diagram. Engineers love these diagrams. So here's my foot opened up, and my foot is moving in the backwards direction along this vector V. And because it's sliding backwards, it's now going to create a force F right at that point, or actually right along that edge that we can see there. And as you can see, the hinge joint is not right down at the surface. It's up a little bit. So there's this lever arm R from here to there. And it turns out to be a lot higher than I actually thought. I thought it was like a centimeter, but now looking at it, it's like, man, it might be like 2 centimeters or more right there. So now it's very clear why it wasn't clear that they were doing it. So I suspect that they didn't get the RL working until about a month ago. Okay, so hello, Mara. How are you doing?
Good. Good.
Yeah, if anyone just saw a previous episode, which was basically our own review of a previous walkabout or field trip at the Automate show, you're going to notice I'm still in the same studio. I'm still wearing the same Robot Mafia t-shirt. So it's clearly still the same day, but this is a second episode we decided to tape which is going to be about the Tesla bot and the dancing videos that came out the past couple of weeks. And obviously, there's been a lot of interest and people asking, what's our take? And I wanted to make sure I had time to go through before I really went too deep in there. And let's go ahead and take a look. And first, what I have to do is see if I can even find where my PowerPoint went. Let's go ahead and get that thing up. Okay, it should be there. And I'm going to go ahead and start that. And this is where your editing is going to work really well.
A few minutes later.
Now, if I try to share, there we go. That's the point I want to share. Okay, so what we're going to do is we're going to talk about the current status of walking in the Tesla bot, or dancing as it may be. And what we need to do is kind of roll the tape back a little bit, is that we have not really had an update about Optimus since December 9th. So it was like nearly 4 months before we finally saw the first walking video. And so just to remind everyone, that's what it looked like. And this was Milan Kovac's response to it, is that, Tesla is where real world AI is happening. These runs are on mulch ground where I myself have slipped before. What's really crazy here is that for these, Optimus is actually blind, keeping its balance without video yet. Only onboard sensors consumed by a neural net running in approximately 2 to 3 milliseconds on its embedded computer. More exciting work happening on adding vision so it can plan better, making the gate look more natural on such rough terrains, making it more responsive to velocity direction commands, learning how to fall to minimize damage when unavoidable and stand back up. Join us to work on fascinating reinforcement learning, imitation learning, foundation nets for robotics, and more, and bring Optimus to everyone fast. We're doing it. Now, when this video came out, John Gibbs, also known as Dr. Know-It-All, and I talked about it. And we both thought they were using reinforcement learning at this point. And I think part of it might have been because you'll notice Milan mentioned it there. But if you look really closely, he's more or less mentioning it in the context of please join us. Not really. It's not. So somehow we thought that they were using reinforcement learning on that. Well, if they're using reinforcement learning, we're going to get a lot of updates really quickly here. 4 months without anything on there. And that was rather curious. And then finally on April 2nd, we see, our latest walk, straight knees, smoother heel to toe gait in arm sway, just chilling around, entirely trained in simulation with RL. So now it's very clear why it wasn't clear that they were doing it. So I suspect that they didn't get the RL working until about a month ago. And yeah, and this kind of, and I just spoke with John Gibbs before getting on here about his take. And he said, yeah, back then he thought so, but now he's beginning to realize that it makes sense. They didn't get the RL working yet. So this is the April 2nd video that he's referring to here, which is the first thing we'd seen in nearly 4 months of any update on Optimus. And here we go. So now it's walking a little bit different than the other ones. He's talking about the arm sway there. We can see a little bit about the, the foot gate and the toe off. It doesn't seem, it's interesting. In some ways, the original one still almost looks better in some situations when it was just going, but this may be a tad faster than what they had. So that's sort of the state of what was going on. And if you look really closely, you will already see that the toe box is articulating. And we also noticed some interesting things about the gate, which I don't think is quite perfect yet, is that sometimes when you'll see the push off, it was like almost right back there. I want to see it again, right there. Okay. Go back to that part and then just kind of look at it yourself again and again. And you notice the foot kind of twists when it does that push off. It's like this, and it seems like it's rotating up at the top of the hip in order to do that. It's not something happening down the ankle. So they're getting what you would usually call like this pronation, that you're coming in and you're pushing in that way. And that's not really considered a good way to do a gait. It puts like a little stress on your knees and everything else. And we're not sure where it's picking that up. And if it's reinforcement learning, either it was told to kind of do that, or it decided that for energy reasons and optimization, that's actually better. So for a human body, you wouldn't want to do that because you're probably going to have sore knees. But hey, maybe it's a little bit different when you go ahead and do it. So that's a rather interesting thing is you notice there's some imperfections. It doesn't walk exactly like a person, nor should it, because, and this is something that Chris Galante has said many times, is that, bone is not muscle and muscle is not motor and bone is not steel. So you got to remember that it was Chris Paxton that said that, that this is reasons we should expect differences as we go forward. Now, here, what I want to do is for you to see the timestamps that I have here. So right there, this doesn't actually go up here, is when it's taking its first step. It's 2 seconds in there, and the next one's at 14 seconds. And the reason we're doing this is something everyone can do at home. You can build your own spreadsheet in which you can put in a start time and an end time, calculate the total time. You can count the number of steps. You can verify that I counted 21 steps from the beginning to the end. This is an estimate here. I'm estimating that the step length is about 16 inches because its foot might be about a foot. I'm not sure if it's 11 inches or 10 inches. It could be size 10 or whatever it is. And it looks like it's almost placing one foot a little bit in front of the other. It's not like a huge stride. Maybe I'm wrong. Maybe it's 18 inches. Put your own number in there. But based on that, this is anyway how many steps per second you're getting. You're getting about 1.7 steps a second, which means it's feet per second. That's about 2.3 feet per second. If you put it in the meters, it's 0.69. Or kilometers, 2.5, and miles per hour, 1.5. Now, if we look at the meters for a second, the standard in factory simulation is that the humans walk at 1.2 meters per second. So that means Optimus has to almost double. It needs to increase its speed still a little bit more to be usable based on what we're seeing in that video. Okay, now this is what Optimus looked like, I guess going back to back last fall, October 17th. And that's rather interesting because it's right around the time of Wii Robot. So we're seeing this update coming on in here, and I did the same thing. And if you look at it, I almost think its gait looks better here than what they had because the arm swing I feel is better because it's using a bit more knee. Now this is 2x, so we don't really care about that. But I'm going to go back to the other one and do the same thing, counting the steps and everything else. So that most likely was not reinforcement learning. That was just using a heuristic algorithm that they've been working on. And now we can have the same thing. So the start time basically starts at 0. It's already walking. End time was right at 6 seconds. And there was about 8 steps in there. And you go through there and you find that the meters per second was about 0.54. So, if you're around 0.6, you double that, you get to 1.2. At there, they were way more than doubling to get to it. So now they're within striking range of it. And so you can see there is a slight improvement here. I think that is about a 25% improvement from 1.2 miles per hour to 1.5. So even if I'm a little bit off because of my step length here, you still see we have a ways. There's no way it's taking a meter long step because that would be 32 inches would be close to a meter. It's not that big a step. So it's something below there. They still have a little ways to go to be really usable for being competitive in the market or in the factory. Okay, now on April 2nd, which is when that first post came out, instead of showing the RL, Ashish said that learned with RL and Sim, deployed 0 shot to reel. That's very important. That means that they were able to get out there, put it in the robot, and it worked first time. They didn't have to do any tuning. We're planning to extend our RL training to manipulation in the coming months with 22 DOF hands. That means they haven't started yet. Okay. The 22 DOF hands, they really haven't been able to start anything yet. Initial results will produce dexterous robot specialists. Okay. My team is also building a generalist robot policy by leveraging robot and generic internet video data. So another area that they're kind of working to get the pipeline up and going. Both are on the critical path to general robot intelligence. Reach out if interested. Okay. So who is this Ashish guy? Well, he's leading AI at Tesla Optimus. Okay, so we can listen to what he says. All right, it's, along with Milan. So then this came out. Okay, just the week past or so, and this is the dancing robot, which everyone has noticed dances better than the human did in the Optimus suit going back 3-4 years ago. I think it's almost 4 years ago now. And so this was a very short video clip. A lot of people get very excited about it, and we'll talk about the excitement in a few minutes here. Um, but there was some reviews. So what were the reviews? Well, let's go to the team itself to see what they thought. And so Milan is like, more coming shortly. The team has been working very hard in the background, entirely trained in simulation with RL. Now, again, he's pointing out RL. He didn't back in December say that. Many optimizations and fixes have been put in place in our sim-to-real training code. The cable is there in case of a fall, not actually holding the bot, since this is an early result, which we will get more stable very quickly. Okay, so let's keep that in mind there. Then Julian Ebart says, Sim-to-real for Optimus getting really good. It's quite handy to have more than a decade of actuator design in-house. So here he is, then quote posting his own colleague, Ashish, Sim-to-real, RL, zero shot. Everything is running on board and real time. Okay, now, so who is Julian Ebarts? Well, he is, the Tesla bot AI lead, so he should know a thing or two about this. And the other thing that he says here is it's quite handy to have more than a decade of actuator design in-house. We've talked about this, that to do RL, you need to have a really good model of your bot, right down to the actuators, and the challenges of using linear actuators and everything else and modeling that right. So when I read that, I was like, oh, okay. So it's taken them a while to really get to the RL. That's why it wasn't RL back in December. They've been trying to build that up and get it right and get it working, which might explain why we're not seeing whatever is the Gen 3 bot, which I don't think they have that many Gen 3 bots out there yet. I believe that the Gen 3 bot is going to be same for the waist down anyway. So it's not like they're wasting it on this, but they're perfecting the pipeline so they can come ahead and begin able to do this. And so this is the next video that came out because Milan said more coming soon. And this is the more coming soon. So now you see Optimus actually is suited up, whereas before a lot of the covers were off. And I kind of joke about this is that, zero shot, but not one shot. I was well, partly I was focused on the Automate show, so I didn't really have a chance to look at this too closely. Someone pointed out that there were scenes that clearly were filmed during the daytime because you could see the sun was out, and others that were at night, and you can see they're in different locations. And so it wasn't one take, but don't worry about that because you'll notice every dance move is very different and unique. So what I suspect is they got something working in the RL and they kind of liked it and say, let's download this one now. And they went over and they shot a video of that. So they get the ballet scene here. Then they go and they do, I don't know, is that hip hop? you know, it's a little bit of a moonwalk going on there. And they shot that one there. See, that last one was in the daytime. This one's at night, and we can see the different scenery. But it really doesn't matter. So one of them was like more tap dancing there, or jazz, and then you get that's me. That's how I would dance. That's dads at a wedding dance. Is what that one is. So they're kind of showing the different capabilities because they're putting down there, which means their RL pipeline is really set up that they could put in something, get it down there, and then they're ready to show it off. So it's not a big deal that it's not a single shot. And in this case, there are no cables. So Milan said they were just there for safety, and now they're like, go for it. No cables. We're confident it's not going to fall. Now, the only concern I have is like, okay, its dance moves are great. I want to see it walking. Please. I want to see it walking so I can count steps. Yes. Yeah. Well, I mean, this is very impressive. And I suspect when we do finally see it walking, it's going to be maybe walking at the rate, at 1.2 meters per second or faster. So Tesla, if you're listening, please, the next thing I want to see is not a dancing robot. I want to see it walking from one side of the room to another and going around and see how quick it can go. It doesn't have to be running. I don't care about running right now. I mean, if they want to show it running, it's kind of running in place.
So what is your suspicion if you saw him walking? What will be different?
It, it should be a lot faster. You see, that previous one was April 2nd. That was a month ago. They just got RL working. And that was like the first test, and it's there. In the 5 intervening weeks, it seems like they've really got everything going, that they're confident in that. The other thing about dancing is everyone says, oh, the dancing robots. And part of it maybe is for because they want to counter what they're seeing from Unitree and Engine AI. So yeah, we can dance too, but it's full body control. Don't look at what's going below the waist. Look the entire body. It's about getting the torso and the movement of the arms. Someone pointed out in one of the comments, and someone said, "Oh, the hands aren't very important." It's like, they are important. I mean, it's not, you don't need the 22-degree frame hands. It's more the arms. They're very important to balance. So when you look at the ballet and you look at those positions, those hands have to be positioned that way. The same way those counterbalances on those big payload robots we talked about in the previous episode are so important to weight balance. It's extremely important. So what we're seeing is full body control. Now, when you're walking, typically you may be, walking and chewing gum at the same time, as the expression goes, meaning Optimus is going to be walking, maybe carrying something, maybe carrying a tray of drinks. Okay. So the lower body has to be kind of aware of what the upper body is doing. It's like, yeah, I got a tray of drink. So whatever we do, let's make sure we don't spill. How do I counter that? So there's and if it's just moving boxes around, whatever it's doing. So full body control, that is the real takeaway here. I am pretty sure it can walk fast, and why they're not showing it, it might be, it just hasn't occurred to them. They think this is cooler than showing anything else, because from here, I think you can extrapolate that it's going to be a lot faster walking. I'm pretty sure that you're going to see decent walking speed right now.
How does it compare to Unitary and NGI and others?
Someone did a collage next to each other, and this seemed a little bit smoother. The others, while impressive, seemed a bit robotic, and this is really impressing me. It's almost got the grace that you would expect. And I still make fun, and at some point I'm gonna put the post out that Optimus is gonna still suck at soccer because it won't be able to kick the soccer ball correctly because the order of operations of the joints. But despite that, it's getting these moves down because it's not that important. I mean, it's not about being able to kick a soccer ball with the side of your foot, okay, when you're dancing. It doesn't matter. You're able to get your ankles and everything exactly in the position orientation that you want. So who knows? There may be a few dance moves it can't quite do, but yeah, look at that. You see, you got to go right there. That's good balance.
So is it come down that they get the exact modeling of the actuator?
That's what it came down to. And this is what Julian Ebart's post there about the actuator design tells me. They finally got it right that they can do zero shot. They're confident in their model. It probably took them a little bit longer to get there, because if they were already doing RL back in the fall, I would have thought that they would have been able to do a lot more. And I don't think it's because they were holding back showing us anything. It's like, I think they didn't have anything that they could show, or it was taking them longer to get it because it's more challenging. And again, that was like a dead giveaway. And I think somewhere else, I think that post might be coming up of some of the others. Okay, here's a little more, no cables this time. Again, it's all real time, zero CGI, fully learned in simulation, and zero shot transferred to real. So again, they're pointing out that, it's the zero shot going on in simulation. And I think RL also. Besides the fact that it's fun, we had made significant improvements to our robot model in sim. Absolutely, of course you did. So in order to prove that they could do this right, it's like a validation. And sometimes these silly things are the kinds of validations you need to do the normal things. You've got to stress it. I mean, this is an extreme situation. So, domain randomization, that's what they talk about, is because we have no idea what the actual actuator on the motor is. We know there's going to be a range of behaviors that it's going to have, of tolerances from manufacturing, from, temperature variations as you're going through the day. It's going to be heating up and everything else. So it has to be able to deal with the fact that the servos are going to misbehave from the ideal. So, but they're going to be within some sort of distribution. So you need to have enough. Another techniques each will directly transfer to more practical situations as well. Robust walking and agile full body control in general. So again, we're seeing that full body control, a very good demonstration of that from the dancing, because we don't want to say, legs do one thing, upper body do something else. It's got full body control is very, very important. We also learned quite a few things in our hardware and tuned our power profile. Well, that's interesting. So they probably found a way to get energy management a little bit better. And again, we learned quite a few things on our hardware. I'm sure they did. And again, it's like really good to have the actuator design in-house to be able to understand this. I hope it's getting clear the test as much. Okay, so here's his recruiting that, every one of these always ends like, please join our team. We would like to have more and more people.
Quick
Yeah.
question.
Mhm.
This actuator made in house, and if I remember, you
Yep.
told
Yep.
there is no linear. Wait a second. If there's no linear,
There is linear. There's half. Yeah. So there's linear actuators and there's rotary. So it's a combination of two. And think about it, a lot of that dancing from you have two hip actuators, which are rotary, and then from there on down, the hip flexion, the knee, the ankles, that's all rotary. And or sorry, not rotary, that's all linear. That's all linear. And so that's very complicated to kind of get that piece right.
You should
And
need
that
the image that remember the one of the episode that they missed the design, exact design of the linear actuation. I think that
yes,
was the
yes, yes, yes. So they're half and half. So they have half linear and half rotary. And again, it comes down to wanting to model that right. So again, Ashish comes in and says that here are some more with music. All of these use the same pipeline. So they've got that pipeline set up. RL training and sim followed by sim to real zero shot. So, all of these, there were different cuts there intentionally, lots of different ones to be able to show what's going on. Our pipeline is relatively robust and requires minimal tuning per dance. So, what dance do you want to do now? Put that in there. Let's go ahead and shoot that. This allows exponential scaling to new behaviors. So they seem to be very excited about what they've been able to do with it. And this, I think, was perhaps one of the more interesting and why I realized that they probably hadn't got the RL working till recently. More dances, all learned end-to-end zero shot from sim to real. RL is back and here to stay. So it seems like they probably maybe didn't have much early success with RL, or there was a debate internally. That's at home, between Julian's remark about the actuator design in this, giving a little bit of insight that they probably weren't sure how well RL was going to work. And now it looks like RL is working so well. It's like, that's it. That's the way we're going to be doing everything going forward. So that's an interesting point. And the other thing that I think probably might have been the reason is I've pointed this thing out again and again, this comment from Jim Pham. And this is back in January, referring to the Unitree bot and what I've highlighted here. Simulation used to be an afterthought. Now it has to be part of the hardware design process. If your robot doesn't simulate well, you can kiss RL goodbye. Hardware simulation co-design is very interesting emergent topic that is only becoming meaningful with today's compute capability. All right. I think that's basically what they're saying. RL is back because they finally were able, because I would say the Optimus kinematics is not the one you would choose if you wanted to make the simulation really easy. There's no
second.
yep.
I remember Tesla, they didn't use NVIDIA Isaac them, and maybe that's the reason that they weren't dependent on them. Is that the reason, or what?
I think they're probably building it all in house. So they may be using NVIDIA chips, but I don't think they're using Isaac Sim. But still, even if they're not using Isaac Sim, Jim's got a really good point there. It's like, it's really hard to model these things if you're not thinking about a co-design between the simulation and that. You probably can do it if you put enough effort. And I think Tesla just proved that you can now do it if you put a lot of effort. But I think that's what was slowing them down a little bit, is being able to do the zero shot by making sure they had the hardware model right. That was the heavy lift as far as I'm concerned. Now, after all of this, pretty much this one image right here from the very first one, the April 2nd, the March 12th, not the one afterward, but the very first one that was put out there, everyone kind of caught this image where they could see the toe box pointing up like that. And that caused a stir out there on the internet of everyone speculating whether A, that this was new, and B, it must be actuated, because the only way that thing could be going up is it had to be actuated. Okay. I'm here to tell you it's not. All right. It's not actuated. And I put a post out there just saying there's been a big flap over a flap. It's articulated. Okay. Not actuated. Full stop. Why? And it just comes down to physics. Okay. It's simple as that. We'll go through it. We'll explain why that is, and for many, many reasons. And at the very end, I think we will actually have the final nail in the coffin. So, the first thing is, I'm just going to be repeating this back and forth. So you'll see the bot is kind of doing a moonwalk. And typically what happens in the moonwalk at that point is your foot is being dragged backwards. Up until this point, we have never seen Optimus drag its foot backwards. It's always been going forward. Okay. And up until this point, no one noticed the articulation in the foot, but it was always there. Okay. And this is a part of a post I put out that for some reason is going crazy right now. It's got like over 100,000 views, in which just reminding everyone that in December 2023, when the Gen 2 bot was revealed, this is one of the images right from there where they say articulated toe sections. They didn't say actuated, they said articulated. Articulated means it's able to move. It's got a hinge in there of some sort, and it has something to put it back in place, probably a torsion spring or something like that. Some sort of flexible unit that'll do it. And you can see right here the angle that the toe box makes back there, which is why they put that in there at that point. We were already seeing that Optimus could walk that way. And you can see this little opening right there, which closes up, which is a pretty big gap that gets made. And you can also see the little fold that happens right up there. That's why I have that little arrow for everyone to kind of notice the fold that's there. These wires you see back here are for the force torque sensing. It's not for the actuator. So that's the reason they're in there.
How it's adaptive for what exactly sense here? What will it adapt in the full?
Well, I think part of it is to get an idea of whether you're tipping or not. So when we stand up, we're feeling a lot through our feet. We can kind of sense what our balance point is. And of course, we can talk about the importance of an actuated toe to balance, which I think is really important. You know, if you're standing and leaning forward, you notice that sometimes you are pushing down on your toes to get the restitution back to where you want to be. That could be done with a strong spring. So you make sure when it's flat out, that the spring only has a lot of force, that you require a lot to just begin to get that opening, which means right now it is trying to push back a little bit to help the overall structure. So you can do that passively or you can do it actively. We have to kind of do it actively because we don't have springs built in to the balls of our feet. So we actually have to pull the tension, but you could crank it up already with these things, and that it already is supplying the torque that you would want to be able to keep the balance. And you might want to also be able to see where your pressure point is. You want to know, where's the pressure point of the force? Is it back here in the heels? Am I rocking on my heels or am I in the ball of my toes? So that's very important to be able to measure, to be able to maintain balance, no doubt about it. So they all have something down there. They all have these sensors. It's not just Tesla, all the others that I've spoken to. So it's well known in the industry to do that. So if you were looking around, you know, going back to that, and then looking at like the video I just showed, which I think was from last fall, you can see that toe off happening right here. So that means you're seeing the articulation. You can see also a little bit of articulation there. A lot, right? And this is the one from April 2nd. This is another one that Humanoid Hub had sort of noticed that is walking up the stairs. We already were seeing it was there. So the signs were all there, just that no one noticed. And again, they went kind of crazy thinking that the articulation was new. I was like, no, they're not changing a whole lot to the Gen 2. This is the Gen 2 platform. Don't change the Gen 2 plate. Change it on the Gen 3 if you want. So right now it doesn't have that. So here is a video, again, from that same announcement that they had of the close-up that you can see it in action. So you can see exactly how that gap opens up and closes. So as soon as the toe comes off, you know, it snaps back into the position and then it moves up. So there we can sort of see it going back and forth again and again to get an idea of exactly how that toe box is working. They're coming with heel toe and it's pushing off. Again, that's December 2023. The walking gait looked pretty good back then. And then, you know, right at the announcement, they kind of nailed it at that point. And it's surprising it didn't improve for such a long time. It's been, you know, over 2 years before we've really seen it get up to the stage. And I think either they didn't think you needed RL because there was a lot of skepticism on whether they should use RL for walking. And then others were doing it in Unitree and those were demonstrating, hey, this works. And then everyone said, okay, maybe we should start to pivot in that direction. So it looks like because the modeling was so challenging, it took a while before they get to the RL.
I want to understand
Yeah.
the part of the actuator modeling they made in house. What was
Mhm.
the challenge? Did you have maybe like you mentioned a couple of things?
Oh, yeah. Well, okay. The first thing, like just these Heim joints are sloppy. You know, just modeling that right, that when you apply the force down here and going through there, what's the articulation going to be like? You know, saying exactly what that's supposed to be. So you have to model everything here correctly in the geometry. So it's partly a trigonometric issue. And then when you go up to the knee, it's even more complicated because they have the Herkins joint there. Even though that linearizes it and makes things a little bit different. So these are complex joints that they have with a lot of additional actions that you have to model correctly, as well as the actuator itself. So they want to know, you know, when they put a certain amount of power in, how much loss is there due to friction, how much of that gets translated into actual forces down there. Because in the end, they want end to end. And that means pretty much it's current in, action out. So they want to figure out what do we have to kind of go right there to get the result that we want at this point. So it's tricky modeling every single aspect. You've got to get all the physics right. Again, moments of inertia, all those, you've got to model that correctly just to get the dynamics right. You've got a system which is constantly reconfiguring itself, which means the moments of inertia that any one of these joints is feeling is going to change from instant to instant. That's also a challenge. Okay, then, so what are the reasons that you want to have an articulated joint? So the Gen 1 of not only Optimus, but many of the other bots out there, they just had a flat foot. No articulation at all, just because they were getting it out. Everyone was pointing out, oh, why don't you have something that's flexible and this and that, or putting on different shoes. And as you can see, I have a flat foot on a flat surface, and the force is evenly distributed over the entire surface area of the foot. Now, as soon as I start to change the angle, like lift up my heel just a little bit, so I have a non-zero angle, the smallest angle, no matter what it is, will instantaneously result in this. At that instant, you go from full contact to contact along an edge or point, but edge and a point is the same thing. One's 0 dimension, the other one's 1 dimension. They have no area. So that means all your forces being right there, you're going to slip. You're just going to slide right away. So you don't want to have a point of contact. You want to have a surface of contact going on there. And so the reason for having the articulation is now when you do that, look, you've got all this, which means you're not going to slip. Now, you still can slip a little bit. I think we all know that sometimes when we're walking, especially in an icy surface, it's that back foot that suddenly slides out underneath us when we least expect it. For that reason, is because the surface area has gone down, but it's still finite. It's not zero. Okay, so now let's go ahead and look at the example of what happens when you start walking backwards with this thing. Now, remember, we get a pretty big gap in the Tesla bot when that opens up. And so if I want you to look at this animation, and so what you can see is that if I drag the foot backwards, I thought I'd put this on repeat. I guess I didn't. If I lift the foot up, so we can see it opens up, and then as I drag it backwards, I end up snagging this corner here, which is going to open it up. And if it's not obvious from this, I'll go to here to this diagram. Engineers love these diagrams. So here's my foot opened up, and my foot is moving in the backwards direction along this vector V. And because it's sliding backwards, it's now going to create a force F right at that point, or actually right along that edge that we can see there. And as you can see, the hinge joint is not right down at the surface. It's up a little bit. So there's this lever arm R from here to there, and it turns out to be a lot higher than I actually thought. I thought it was like a centimeter, but now looking at it, it's like, man, it might be like 2 centimeters or more right there. And we know F times R produces a torque T, in this case, in the counterclockwise direction, which is going to cause this thing to rotate, and probably in excess of whatever the spring constant is that they have there. So the torque is going to exceed whatever the closing torsion is that's coming from that spring. And that just results in it opening up like that. So that's going to happen. And so long as you're dragging that foot back, it's going up. So it's not actuated, it's articulated. So I say the physics proves why that happened, that flap.
Quick question, maybe the joint, I know it's physics, but the positioning of the joint and the size of the joint, do you think, because you mentioned the torque, so how do you make sure?
Yeah, I mean, part of it is biomimicry, I'm sure. It's similar proportion to a human foot. And yeah, there had to be a good selection of what that spring force would be. So they're going to have to figure out when they're walking exactly how much they would like it to bounce back. And so that's going to come from their modeling to figure out what it is. And so you're going to have a closing torque that will kind of keep it in place fairly well, fairly stiff. And as they go up, of course, the more displacement you have, the harder and harder it's pushing. And then if you go too far, it's going to push. And that's what they want. And then what that's going to do, that's going to store energy. And then when you go out of that and then into the swing phase, so this is when you do something they call dorsiflexion, is that as you start to walk, your ankle is pushing down. And as it pushes down, that's happening, which is kind of helping the leg to lift up, lifting up the whole body. And then at some point, you need to transition as it comes off, and then it's going to close. And that's where, you know, you're going to then have that problem. Say, well, you got a flat surface here and another flat surface here, which means you're going to have that same old problem. You're going to kind of tip up to a sharp edge. And that's why the front parts there usually are not flat. They have like a little rolled surface to roll off, and they're a little bit squishy so that you're pushing down and get it. And that's because that's the same way an automobile tire works. An automobile tire, in theory, if it's perfectly round and the surface you're on is perfectly flat, you only have a line of contact. You have no surface area. You should not have any traction. Well, they're deformable. And if you look at any car and you go out there, you'll see it's kind of looks a little bit flat down where the road surface is. And it's designed to be that way. That's why they recommend a certain inflation pressure to make sure you get the maximum amount of grip that you kind of need for the car. And if you overinflate your tires, you're going to slip a lot more. So it would be the same thing. You would make the front of that toe box out of some sort of material that as you're going around there, especially to the front, you make sure it deforms so you maintain a little bit. But at that point, it's not as critical because the body's expecting to lose contact and is prepared for it. It's usually when we're taking that stride and we're not expecting to be on ice and all of a sudden, whew, we go off because it's the worst timing. We're expecting it to be able to support us. So at that point, the transition is taken care of. And again, that's something it's going to learn in RL. You're going to model the physics in such a way that it knows, oh, you keep falling down because you're not aware of that transition. And then eventually it figures it out and says, oh, okay, I'll be more careful when I get the foot to that attitude to make sure I don't fall down. So that's how it works. And this here, I mean, it's like when I grabbed this morning, the view count on this was 66K. It's now, I think, over 110,000. So it's nearly doubled since then. And I think it's doubled because of Anon. And so this is the post I put out there just saying, the articulated toe sections have always been in the Gen 2 Optimus design since December 2022 reveal, just not obvious until the gait improved. And so I showed again the images that we just had demonstrating that. And Anand basically says, an articulated toe, even a well-tuned passive one, adds a lot to improve the gracefulness of the gait. It also becomes important while balancing weight transfer and kinematic reach for going upstairs. It's actually obvious when you just walk and pay attention to what our feet do, but we don't think about it most of the time. The human body is amazing. I love that because this is what I've been telling all our viewers is that you can be a biomechanist. Go out and study what you do. Start thinking about what each joint does and what happens if you freeze a joint. Can you get through the day without that joint or not? Or it's like, yeah, you can get through, but it's very, very difficult. So again, he's pointing that out, that we do that. We don't realize that we're doing that. And okay, so who is this Anand guy? Well, he's someone who's been with Tesla for over 10 years and has worked in he's worked in projects going back to like the Model X and S and everything else, battery. He's also been in the Optimus project. And I think last week was his last day there. He's now moving over to Zipline. And yes. And if you actually follow a lot of the people on the Tesla bot team, like Julia and like Milan, like Ashish, you'll notice they don't post very much. Every now and then there's something like that. And it's probably because they're very busy and they also want to make sure that they just kind of post things that are professional and nothing more. They all stay quiet. Now that Anand has left, he may have felt a little bit more freedom here to actually go ahead and post. So this is like the first time I had seen a reply from anyone in the Tesla bot team. I'm like, oh, wow, this is great. Someone noticed. And I look at it. Oh, my last day was May 15th. They're like, oh, okay. But he's going on the zip line, which I think is going to be pretty cool. And he makes really, really good points. And the main point is like, if anyone should know, it should be him. An articulated. Okay, he's not saying an actuated. He's saying an articulated joint, and he underscores even a well-tuned passive one. I think he's just laying it right out there. Yep, it's articulated, not actuated. End of story.
Scott, yeah, I think it's really interesting because I'm coming from soft robotics, but I think it's come down to geometric intelligence. In nature, like there's certain design, just take advantage of intelligent geometry, nothing else. Take everything for free. without control, without anything. And that's the beauty of maybe geometry, just to make intelligent geometry or architected geometry or
Exactly,
whatever
exactly.
like
Just
that.
study geometry and you'll be able to figure out what's going on. Use things. You can get a lot done with passive stuff. So I love analog things. Don't overdo it. Don't overthink it. Our body does a lot of things almost, what they say, like knee jerk reaction kind of things. That you have a lot of these built in reflexes, and that you think, well, they're actually, well, a lot of cases, what's happening is your muscles and ligaments are more or less storing energy and returning energy, and the body can't make a normal spring mechanism, so it makes it a different way. So don't confuse what's going on there with necessarily being actuated, but is something that is more of a passive, instantaneous response to what's going on. There are some things that, yes, we have usually the more motor control thinking about it, and others that just happen reflexively. And that's where you should use spring. Mhm.
Sorry to bring this one, but I think a bot was in Max Planck Institute in Germany. I think this was 4 years ago, and they did the bird
Yeah.
bot. I don't know if you
Okay.
heard about
Yep.
this bot. And I think in the foot they have this kind of
Yep.
compliant or articulated joint when it's run and inspired, I think, by one of the birds. Just like I think they have someone from biology, and they I think they take exactly an inspiration this Japan joint when it's run or going over obstacles just for free. This
Yes.
kind of articulation.
Yeah, yeah, I seem to remember something like that, and there's a lot of clever designs that you can do where nature has figured out a way of they could enter. Nature is in a perpetual energy crisis. That's what it comes down to. Everything through evolution has been able to figure out how to solve an energy crisis. And you need to make sure you don't expend more energy than necessary to do whatever you have to. That's why nature figures out some way or some trick to take advantage of physics to be able to store energy or return energy or get some sort of mechanical advantage on something that they could do amazing things. So biomimicry is very, very important because there is a solution out there just waiting to be applied in many places. Now, this image here we're seeing came from the quarterly report showing the assembly line for what is going to be this pre-production version of the Tesla bot. And we can see they're already fitting down here the new hand, the 22 DOF hand. And we can already see some changes around the neck area and in the torso. The chest plays a little bit different. The shoulder is covered a little bit different. So kinematically, it's all the same. It's just that they've tightened up a few things. Maybe the actuators are lighter and tighter, like they say. We don't have a really good image of what's going on down below. Of course, the legs are all made out of black color, so it's really hard to see. We can see a little bit over in some places. And from what I can see when I zoom in and everything, it doesn't look like it's any different than the Gen 2, probably maybe with little tweaks here and there. I'm pretty sure that the waist area and everything is the same. So that's why we're not seeing the Gen 3 bot. And I think, we can see a little bit of a close up here. So, we can see a little bit better the hand. It, I think I got one with slightly better contrast that it was able to see enough that I was pretty convinced that the configuration of the waist is exactly the same. It hasn't changed. It's not like they've gone to a far design all of a sudden on us or anything like that. So it's all pretty much the same.
Just remind you, I don't know where they are selling for because I think Ellen said like $30,000 something like that. And who's buying them for
Oh,
now?
what
Do you
what,
have
what
an
did he say
idea?
the price
Who
was?
will you? 30,000?
Someone
It
is
was
saying 30.
30,000
I
if
don't,
I
they're
remember,
not going to
or
sell.
less.
He might be saying that they should be able to make them, or people have asked, what would it be? And it's more or less, it shouldn't be more than a car. And if you figure a car is somewhere around $30,000, the manufacturing cost, it's hard to say what it's going to be until they really scale it. So the initial ones, I'm sure they're under the 100,000. They're probably under 50. They might be close to being able to build these for 25 to 30, and it could probably go down from there. I'm pretty sure they could bring it under 10,000 eventually when they get those numbers. The question is, are they going to sell them for that? And they won't at first. If they do, there should be a shareholder revolt and lawsuit because that's financial malpractice because the value of the bot is so much and the demand is going to be way beyond supply at first. So they can be easily leasing these for 100,000 a year. And I'm pretty sure that's what they're going to do. And not just them, they are all doing the same thing. Agility effectively at their hourly rate, what they're doing, it's also probably coming close to $100,000 if, if Digit is working 24/7 or, 22/7, whatever it would be. So Companies are willing to pay that right now because they can't find the workers, and it's actually a little bit cheaper than the labor force that they would have. So until you get really large numbers of these bots out there, and I mean, like, you would have to have probably close to 100 million worldwide or more before it starts making a dent that prices have to come down, because that's about what the labor shortage is worldwide, is like all these positions that people would like to fill. Now, it doesn't mean it can fill all those positions, but what it could mean is that it by filling certain positions, people can go and fill those others because they have the skills to do that the bot doesn't. So it's like you can move these resources around that will now help fill a lot of those that the robots can't, while maybe he's taking over some of the others. So when you get to that, and that's depending upon how everyone believes what the scaling is going to be, is like maybe around 2030 when you start to see the 100 million bots full. I mean, from everyone, not just from Tesla, from everyone. Tesla could be at 1 million plus at that point if everything is going right. So potentially they could be building at least 1 million a year at that point. And then you have all these other bot companies that'll be the same thing. And then within a year or two after that, you're starting to see they're producing about 100 million a year. So early 2030s, that's feasible. Okay. So again, I want to caution everyone, that's feasible. It's possible to scale it. Whether that happens, it doesn't matter, because I've said this before. It doesn't make sense to scale a sucky bot. So if the bots can't do anything, if they're horrible, if they're breaking down and everything, don't scale yet. Get them fixed, get them right. And then when they're a good product, then you can go ahead and scale. But there may be some areas where a less than ideal bot is already worth scaling because it's a very narrow application, and you can go ahead and do that. So I think, believe it or not, that's my last slide. Or, oh, I think, yeah, the one thing I just wanted to, this is here to remind myself, we did have a little chat with Robert Scoble about a week or so ago, and he talked a little bit about Foundation, which is another robotic startup with some people that come from a variety of other humanoid companies, including Tesla. And Sankit was sort of asked, the typical question, why not wheels and everything else for it? His feeling, and I think he's right, is that bipedalism has kind of been solved, and eventually it will be so good, it'll almost be cheaper than using wheels. And I know it sounds crazy. It's like, really? It's like at some point they'll be able to scale that it's just easy to put legs on your torso than it is a mobile robot, because mobile robots are not quite, wheeled mobile robots are not as easy as some people think. They're more tippy than you think. You really do need to almost put the wheels on legs or have some sort of suspension system to get over bumps and everything else, because even what you think is a prepared flat surface for wheels turns out to not be. All you need is, like, a house, like a carpet. Check out what happens when your Roomba goes from a flat floor to one that you suddenly threw an area rug down there. Sometimes it has a hard time getting, especially if it's very thick, or any other things like that. Wheeled vehicles do not perform that well unless you have some way of being. And at that point, you're making it so complex, you may as well go to bipedal. And bipedal literally has a smaller footprint, so you can get around and balance and lean forward and do all the other things. So I kind of agree is that the argument will almost take care of itself when walking is just done so easily with these things, that it's just cheaper, as a cheaper solution than going ahead and using.
And so, like, I think the video that you shared, I'm not sure which the company, the wheel that flipped and become horizontal and vertical. I think.
Yeah, yeah. I can't remember the name of the company. Is another company in China, because there's so many of them, and pretty much it came out stomping, and its feet were literally wheels like this that were on the floor, and then it would jump up, and then the wheel would all of a sudden pop into position, and then suddenly it was able to go around like that. So it's it's
Yeah, it's okay. It's impressive the switch from horizontal to vertical, but the
yeah,
way it moved, when you explain what already the articulated joint, it makes sense there that this is not to me.
it's one of those that um as a proof of concept, it's interesting. It's not what the final version is gonna have to look like, because I'm sure just taking a wheel and turning it over and stomping around like that is not ideal for it. So you'd wanna somehow change the side profiles of those to behave a little bit more like a foot, and maybe getting the ankle. So there, yeah, I think they probably rush it. It's like, "Just get some wheels from somewhere, and we'll go ahead and put it on there." So I would definitely design it
Why
differently.
this engineer, whoever designed that, decided let's do something different? Is it easier for the control? Is it whatever? What is the rationale?
I think it's just because of that argument of, wheels versus bipedal and putting in there. And certainly if you look at the robot dog that Unitree has with the wheels on it, it's just incredible. I mean, and then you just lock the wheels in place. So I'm not sure if popping around sideways is the solution, because with the wheels already in place, they almost can be a pretty good foot. You just lock them and they walk around okay. They're not quite as flat, but in some ways they almost sound better because they're tires, whereas all the other robots are coming down with this hard steel, clang, clang, clang. So, yeah. Now if it's deformable, so this is the thing is like if someone can figure out how to take that wheel and like deform it, so now it's not round, but it takes more of a profile down the bottom, and then when you're ready to go wheel, it just suddenly goes boom and just kind of gets in that shape. So you get some shape more, and that's where your self robotics comes in there, Marwa, is designing a foot that it just boom, this goes out and then pops back in to the right shape. And then I think that's the solution, not this other thing of pop around. Because I agree. It's like, okay, what they're doing is showing the idea of having something that's a foot and then having something that can flip over to be a wheel. And they're looking at it like I suppose they could make like a nice side profile there that makes it very much like a foot, even though it's a bit wider than I would like it to see. But maybe you play with that design a little bit, and then it pops up, and now it's clearly a wheel. It just by changing direction as opposed to having to change the shape. So, but the size of the wheel has to be at least that. You don't want to go much smaller because anyone that's dealt with small casters knows, a small wheel is just terrible at going over anything. And that's about the minimum size wheel that you want, but you don't want to have something that's as big as a bicycle wheel because those become too unwieldy, as far as wheels go.
This is maybe something we can discuss. I think there's a lot of things we can be done there.
Mhm.
Uh, but
Yeah,
what
yeah,
take away for me, I think
yep.
the articulate joint. I think
Mm.
more of that we can have for
Mhm.
free using passive dynamics or anything like that. So yeah, and modeling. I think it's just coming to the actual modeling and simulation and to make your
Mhm.
lyrics. I think that's also important to take away. I really enjoy it. It was really great. And I can't wait to see what's next. So I don't know what's next will be, but it was great. I really enjoyed it. Learned it something.
Yeah, I think we've got some interesting interviews coming up, the next couple of weeks, Archimedes, and we also are gonna be looking at the orbital drive, which is also an interesting solution to something I proposed before, the Quaternion drive. That interview will be coming up. We've also got the interview with David Rager of Nura coming out. We'll probably have some, yeah, and we'll have a follow-up at Automatica as well, where we get to see the robot live. Yeah, I think there's gonna be a bit more of getting a lot of interesting people reaching out, wanting to talk to us on what they're doing. It's exciting. And, and then I'll still have, like, some more lessons. I'm gonna be talking about the Piper condition at some point and getting back into kinematics for some people.
Okay, there's a lot of things, interesting things, and it's a lot of, to be honest, so much excitement. To be honest, it's just
Mhm.
it's exciting time I think for robotics now. So, and I think you have been familiar with all the things like 30 years ago, and most things are just coming up now, and that's crazy.
Yeah, yeah. There's been a lot of interesting designs, some of which people are resurrecting, not realizing that it already was sort of done and that but it's not bad to resurrect some of the designs because at that time, they may not have been successful because certain technologies just weren't ready yet. Either computing technology or servo technology or being able, the sensors they might need. So there's nothing wrong with taking a look at some of the ideas people came up with because they may actually have a second life that we're just not aware of.
Anyway, I'm so excited. It's just, yeah, it's all the fun, and I appreciate your investigation. I think keep more of that. I think, yeah. Anyway, I know that you're doing this to help many people, and I think I appreciate that to get this knowledge to many people as much as possible. So I appreciate that.
Okay. Yeah. So you're welcome. I'll let you get back to the rest of your weekend. And next time everyone sees me, you should be back at my studio down in Florida.
Safe travels.
Okay. Thank you, Marwa.